Okay, right. So, what's to do with this thing, right? So this is kind of like my third time recording this because for the first one I didn't know what to say for the intro, and the second one, um, well, it was just extremely awkward because again I didn't have anything to say for the intro, so I'm just gonna skip the intro altogether, and I'm gonna go directly into actually evaluating this, which I think is better because it saves time. No one likes to hear me yap, so here we go. We have a trigonometric integral, very trig heavy, because I was sort of experimenting with trig integrals because it's something that I do embarrassingly often, like embarrassingly not often. Like I rarely deal with trigonometric functions inside, integrals. The most recent one I've ever done was the contour integration one, but that was mostly about imaginary numbers and imaginary integration. I'm pretty sure I'm pretty sure I mispronounced a lot of words there. Point is, we now have this. We have the integral of the tangent squared times the natural log of the tangent over the fourth power of the secant. Now, the first thing I did, right, when I was experimenting, I changed the secant because basically my thought process was I wanted to change everything to the tangent. Now, here we have the integral from 0 to pi over 2. The tangent squared x natural log of the tangent divided by. Now, what I did was I did the fourth power kind of on purpose because I wanted to have at least a sort of secant squared because I can change that into tangent, and that's exactly what I did. So 1 plus the tangent squared x all squared dx. And you can verify that 1 plus tangent squared is equal to secant to the fourth. So now we have this integral. So what are we going to do for this? Well, this is sort of like this was sort of a byproduct of something that I was originally wanting to record, which was something about the old Putnam exam, the old Putnam integration problem, which went something like this: the integral from 0 to pi over 2, 1 over 1 plus tangent. In the exam, the tangent was raised to the power of square root of 2. But what I wanted to do was I wanted to change that to some random exponent. Just I need a good variable. Phi, I guess. Recently, I've been using phi a lot because I like the sort of circles that I have to make. Not circles, the overall curve itself. It's very comforting to write. Point is, I was dealing with this sort of integral right here, and my thought process was to differentiate this and I did this because if you did differentiate this, if I were to set this to be defined as some function f in terms of phi, then that would mean that f prime of phi is equal to the integral from 0 to pi over 2. We have so for we're just gonna take the secant, right? We have the derivative. Take the secant is not an actual mathematical function. We're going to take the derivative. First of all, we have this reciprocal, which we know the derivative of. It's 1 plus, well, first of all, it's the inside, 1 plus tangent to the alpha to the phi. I get characters mixed up now. I have no idea why. Squared, and we have a negative 1 up top. And then the chain rule, so we take the derivative of the inside. 1 goes away. Tangent of 5x, that's kind of like a to the phi. Because a is just this tan x over here, and the derivative of a to the phi is a to the phi. So we have tangent to the phi's power of x times the natural log of a, which is just a natural log of the tangent. And now you can sort of see the similarities. We both have a tangent to some power, and then we have a natural log of the tangent, and then we have a 1 plus tangent to some power squared. But the one thing that's changed is this negative. So what we can just say is that this thing is equal to negative the function, this integral function, prime evaluated at 2. Because those are the actual powers that we get. Okay, so this is the sort of more compact notation. We have the function defined as this integral. Now we have to figure out what this function is. Now this is sort of like an opposite of a Feynman's trick. The reason I didn't do that, the reason I didn't do that because I would have to take the antiderivative of tangent to the the 5th power of x, and then divided by 1 plus tangent to the 5th power of x squared. It would just be an absolute mess. So I sort of plugged in numbers and kind of, I was lucky that I got these numbers. Point is, we now have this integral. If we can solve this, we can take the derivative at 2, and then we would be all done. That would be fine. So we're going to first invoke a sort of substitution that would essentially flip this. So what we're going to do is, this is now equal to the integral from 0 to pi over 2. We have 1 plus. We have the tangent. Tangent to some 5th power. I need to say, like, phi is a bit dodgy to pronounce. And then here we're going to put pi over 2 minus x, because, well, we can. We invoke a sort of substitution that sort of flips the sort of function, and then around pi over 4, and then that works because symmetry, dx. And now what we're going to do is we're going to sort of add these together. But well, the first thing I'm going to do is I'm going to invoke another trigonometric fact, which is that the tangent of pi over 2 minus x, or essentially this entire chunk right here, this is equal to the integral from 0 to pi over 2, 1 plus the cotangent, because the cotangent is just tangent of pi over 2 minus x, to the 5th power of x. And now we're going to invoke another sort of trigonometric fact. The cotangent is just the reciprocal of the tangent. In this case, we can write it as, and I apologize if I'm going to make my fraction incredibly ugly with this next thing I'm going to do. 1 plus 1 divided by tangent to the phi. Now, honestly, if you've been around the block on the sort of YouTube calculus block, this thing would just be absolutely trivial, because a lot of people have done this before, and I realized that, well, I'm probably incredibly late on mentioning this. The point is, the next thing we're going to do is we're going to multiply top and bottom by this tangent to the phi, so we don't have this ugly fraction over here. And then we get the integral from 0 to pi over 2. Top is tangent to the phi, x, divided by, this becomes tangent to the phi, but I'm going to put it to the back because I want it to match. We have 1 here because it's this, and then plus tangent to the phi, x dx. Cool. So this function, this integral here, is now equal to this thing. And this is nice because if we were to add these two up, we essentially, because these bounds are the same and the denominators are the same too, we could just add up the numerators and we get 1 plus the tangent to the 5th power. So this is equal to, we're going to do 1/2 the sum of these two, because that's how it works, the integral from 0 to pi over 2 of 1 plus, because as I said, you can add these two together, tangent to the phi of x over 1 plus tangent to the phi of x dx. And then this thing cancels out, so it's just the integral of 1 dx from 0 to pi over 2, which is just pi over 2, times 1/2, we have pi over 4. So I've kind of said this, but this integral I've seen so many times that I kind of felt like maybe I should just skip this, but then I thought, you know what, if I skip that, this entire thing and this entire video would just be like a minute long. So I decided to add a sort of quick solution development, right? But here, the point stands that this function is now directly equal to pi fourths. And this is incredibly important for our original problem, because what it means is that this function is a constant. It doesn't matter which phi you put into this. It could be square root of 2, like the exam. It could be, well, 2, like we are going to do. Or it could be like 10,000 and then 19,421. It is all going to be for pi fourths. And the amazing thing about constant functions, and namely constant functions in particular, is that their derivatives are all equal to 0, because the point of a derivative is how it changes, but this thing doesn't change, so its derivative is equal to 0. So at this point, it doesn't care what I do. I could have done like tangent to the 19,421th power times natural tangent over secant to some power, whatever. The point is, it doesn't matter what I do. It doesn't matter what I'm going to put into this. This is always going to be equal to 0, because it's just the derivative of a constant function, and negative 0 is 0. So this is basically, this is the sort of very interesting result that I got. And to be honest, the reason I put 2 in here was because if I have 2 in here, I can now invoke trigonometric identities that would make the secant here. But other than that, I could have done any number I wanted, and it wouldn't change. So here's the thing. To solve this is kind of like to solve every single integral of this form. And I like those sort of generalizations, so this is cool. Also, the 0 here, I just want to say this because, well, I haven't done a lot of exploring on this integral, to be fair. I wonder, because of this 0, is this function, does it have some sort of symmetries? Because maybe if you shift this back by pi fourths, maybe you get an even function, and because it's a symmetric interval, maybe I give 0 as well. Is there some sort of other explanation to why this is 0? Because this does feel pretty miraculous. Well, that's gonna be pretty much it. We've only actually been recording for about 12 minutes, so it's a quicker video. It's not a lot of content, but I just wanted to share this because I thought it was pretty cool. Anyway, I'll see you when I next upload. Once again, I can't give any promises. Right, I'll see you there.